Hello everyone. In today's discussion, we discuss a very interesting question, and this question is asked in the TIFR-CAM PhD entrance exam 2025. And this question is from the functional analysis part. Here in this question, given that C01 is the inner product space. C01 is the continuous function space, and it is this space is associated with this inner product, and it is defined in this way. Inner product of the function f and g is equal to integral from 0 to 1 f of x into g of x dx, and this space is denoted by the notation capital X. Now we define a mapping from the x space to x space. It is called the operator, and this operator is defined in this way. So it takes the continuous function f to the integral from x to 1 f of t dt for every f belongs to this continuous function space x. Okay, and what is asking in the question? In the question we have to check whether this operator is surjective, means it is onto or not. And in the second option we have to check that there exists a bounded linear operator u which maps from x to x such that u composition t is the equal to with the identity map. And in the third option we have to check that the image set of that is tx is dense in x, whether it is dense in x or not, and whether we have to check that the image set tx is closed in x or not. Okay, we have to verify all these things. First, to know whether t is surjective or not, first of all we have to identify that image set tx. Okay, and we are claiming that this image set tx is nothing but this set. This set contains all the differentiable function one time continuously differentiable functions such that f of 1 is equal to 0. One can ask how to think that from where you are getting this intuition that this image set is equal with this set. First thing, here you have to note that the function operator t is defined in the integral form, and it is integrating x to 1 f of t dt, but here f is coming from the space x, so f is a continuous function, so it is continuous. Okay, and we are integrating a continuous function, so we get what? So it will be differentiable by using the fundamental theorem of calculus. We know that if we integrate a continuous function, its regularity will increase to 1. So we get at least that this function, if tf is equal to g, so we expect that this image function g is at least one time differentiable. So from this intuition it is coming. And if you observe here that if you take x is equal to 1, if you put here gx is equal to 1, if you calculate g of 1, so it gives what? tf1, and it is nothing but the integral from 1 to 1 f of t dt, and we know that the integral from 1 to 1 f of t dt is equal to 0. So here we are getting g of 1 is equal to 0. So the image g is a differentiable function, and at the point x is equal to 1 it is giving 0. Therefore we are expecting this should be the image set, and we will prove it mathematically. So to say that tx is equal to what? ts is equal with y, we have to show what? We have to show that tx is the subset of y and y is the subset of tx. Then we are done. First, therefore we are claiming that tx is subset of y. So let us take an element in this image set tx, then we will show that this element g also lie in this set y. Then we are done for the first part. Okay, so since this element g belongs to tx, this implies that there exists an element f in the domain so that tf is equal to g. This is the definition of an element in the image set, and this implies what? Gx is equal to tf of x for every x, and it is defined in this way: integral from x to 1 f of t dt for x belongs to 0 1 close interval. Okay, and this gives this one. Okay, Then if you rewrite this expression, it can be rewritten in this form. Okay, but here this quantity, it is an integral from 0 to 1 f of t dt, so it is a constant quantity, so it is a real number, and the latter one is integral from 0 to x f of t dt. And here f is a continuous function, so we are integrating from 0 to x. Okay, so this expression is at least differentiable. Okay, and it is a real number, so the whole expression is also differentiable. Therefore we can differentiate on both sides. Since g is equal with this differentiable function, so g is also differentiable, so g dash is equal to, here this expression is constant, so it gives 0, and this here we will apply, in this expression we will apply the fundamental theorem of calculus, or you can apply or simply the Leibniz rule. Okay, Newton-Leibniz formula. Then you will get this expression. And here observe that g dash is equal with this f, and f is a continuous function, therefore derivative is continuous. So we get that finally we obtain that g is differentiable and its derivative is continuous, therefore g belongs to lie in this space. And this space has a meaning, that this space has a meaning means this space contains all the continuous functions whose derivative is also continuous. But we have already shown that g is differentiable and its derivative is also continuous, therefore g lie in this space. But we also have to show that g of 1 is equal to also 0. But if you, it is coming directly, if you put here in this expression g of 1, it gives integral from 1 to 1 g of t dt, not a g of t, here it is from the f of t, it is mistaken, it is f of t dt, so it is equal to 0, therefore g of 1 is equal with 0. So we get that g belongs to C101 and g of 1 is equal to 0, therefore g lie in this space y. We took the element g belongs to tx, but it lie in this space y, therefore tx is subset of y. One side is proved. Now we will move to prove that y is subset of tx. This one we will prove. How to prove it? Therefore we take an element from the space y. Here it is mistakenly written y x. Let an arbitrary element, it belongs to y. Okay, this one is the y. So since h belongs to h be an arbitrary element which belongs to y, our target is to show that h belongs to tx. Okay, then this inclusion will be proved. So since h belongs to y, it is the definition of the set y that h lie in this differentiable function space, and h1 is equal to 0. Since h1 is equal to 0 and h is differentiable, so we can write this by using the fundamental theorem of calculus, because if you, its integral value gives what? Integral value gives what? H of 1 minus h of x. Here there is a bracket, so if you open it, so you will get hx. So this can be written, since h is differentiable, here the derivative is coming. And then in the next step we put the minus sign inside. Okay, and this expression can be written in the operator form, this, because it is the definition of the function operator t of t, operator t. So this relation is true for all x belongs to 0 1 close interval. This relation is true, therefore this implies t of minus of h dash is equal to h, and we know that minus of h dash belongs to x. Why? X is the continuous. We know that our h belongs to c1. C1 means its derivative is also continuous, so h dash is continuous, so the negative of h dash is also continuous, therefore it lie in this space. So we get a point in the domain set, and its and t operates on this element and gives h. This implies what? H is the element in the range set, so h belongs to t of x. Initially we took the element from the set y, but we show that this element lie in this space Tx. This implies what? And H is arbitrary, so y is subset of Tx. Therefore we finally proved that y is subset of Tx. From 1 and 2 we obtain that Tx is equal to y. So we proved that this Tx set is this one, means the image set is this one, and we know that this space is not equal with x, means this is not equal with continuous. There are so many continuous functions which may be continuous but not differentiable, so those functions do not lie in this space. So this space is not equal with the x space, therefore T cannot be surjective, so this option is false. Okay, I hope that up to this point T is surjective is false is clear to you. Then we will move to the option C and D. We will verify, because we have already identified what is the set Tx. Now we will check whether Tx is dense or whether Tx is closed. Okay. Before going to say about dense or closed, one thing you have to always remember that in your higher study or from your future study, you have to remember this point. What I am going to say is that whenever there is a term dense is coming, then you have to identify denseness is with respect to which norm. Norm should be specified in your future study, because in the previous studies, mainly in your BSc or MSc time, maybe, but in the functional analysis you have to be careful, because in your BSc time we are dealing only with the standard Euclidean norm, but in the functional analysis study there are so many norms, maybe LP norms, SOUP norms. So therefore you have to check that this space is dense with respect to which norm. This norm should be identified, but here inner product space is given, therefore we have to identify the exact norm exact norm associated with this inner product space X. Okay, and the standard norm in the inner product space is defined in this way. It is the inner product of f comma f square root of inner product of f comma f. So it gives what? This L2 norm. So this space X is associated with the L2 norm. Okay, L2 norm means it is written in this form, L2 norm, and this norm is this one. Okay, now we will check that whether this Tx is dense in X with respect to this L2 norm. Okay, and this denseness comes from a very standard result. It is a very standard result in the functional analysis. It is your homework to prove this result. This result is saying that this set it contains all the infinite time differentiable functions such that f of 0 and f of 1 are vanishing, means f of f0 is equal to 0 and f of 1 is equal to 0. Okay, means this space contains all the infinite time differentiable functions, means it contains all the smooth functions which are vanishing at the boundary. Okay, this set is dense in C01 space with respect to the pth norm, LP norm, and p is from 1 to infinity, and infinity is not included but 1 is included. Okay, so but our image set Tx is a bigger set. Z is subset of Tx, because Z contains all the smooth functions, so that this f of 1 is equal to 0 and f of 0 is equal to 0, but it contains all one time differentiable functions, so that f of 1 is 0. So number of conditions is more in the set Z, therefore Z is subset of Tx. Since Z is dense, and here in our problem p is equal to 2, we know that this set Z is dense in this C01, means Z is subset of C01 and Z closure is equal to C01 with respect to this norm, and here the whole space intersection with this space means here all the discussions are going on the whole space is X. It is a whole space, so we are talking always with the intersection point. Okay, means I am saying that here this set Z is dense in this space C01, means Z closure is equal to C01 with respect to the L2 norm. But here the main point is I am emphasizing why the subspace topology, because if you calculate the exact closure of Z closure, it gives equal to L2. But here we are not dealing with the space L2, but we have to intersect with this C01, then it gives the closure, because we are checking the denseness in the space whole space X. Okay, keep in mind, do not confuse that. Maybe those who know that CC infinity functions are dense in the space L2, then they will confuse. So to avoid the confusion, I am emphasizing that here the whole space is X. So whenever you are calculating the closure, because its actual closure will gives the if you calculate the actual closure of Z closure with respect to the norm L2, so it gives the whole space L2. But here we are checking the denseness with respect to the whole space X, so you have to take the intersection X, so it gives equal with X. Okay, since L2 contains all the continuous functions in the bounded domains. Okay, so therefore our this closure is equal with L2 intersection X, and it is nothing but X. Therefore we are saying that Z closure is dense in X. Okay, since Z closure is a smaller set and it is dense in X, so but Tx is a bigger set, therefore Tx closure is also equal with X. Okay, so Tx is dense in X. So this is the argument. Since Z is subset of Tx and Z closure with respect to this norm is equal with X, but I am emphasizing that actually this closure is equal to L2, but since we are our whole space is X, we are taking the intersection with X. Okay, so it gives equal with X, and we know that our this space, therefore this closure will be bigger than, since this is subset of this and this closure is bigger, and therefore this closure intersection X is equal with X, because this closure contains this space X. Therefore this implies that Tx whole closure with respect to the L2 norm is equal with X. This implies Tx is dense in X. But we know that Tx closure which is equal with X is not equal with X. I have already told this thing. This implies that Tx closure this implies what? This implies that Tx closure is not equal with Tx. Therefore Tx is not a closed set. So in this discussion we infer that Tx is dense in X, but it is not a closed set. So we get option C is true, but option D is false. So we are left the option B. Now we have to check this option B, whether we can find a bounded linear operator U which is mapping from X to X, so that U composition with T is the identity map. Whether we can find it, let me check. So suppose we can find, we will prove that that we cannot find, but where you are getting the intuition that you cannot find such a map, because if you closely observe this U composition T is what? U composition T F is equal, you are saying identity, but TF is equal to what? The integration. and u is the means the operator t is integration of f. Integration of f is equal with f, and here the operator u. So this operator u must be a derivative operator. Derivative integration cancel, so we will get the main function. Okay, so we are expecting that this operator u should be the derivative operator. And if you have already studied the functional analysis topic, you know that the operator derivative operator is always a unbounded operator in the continuous function space or the differential function space. But the integral operator is a bounded operator, but the derivative operator is always a unbounded operator. So this u cannot be bounded. So therefore I am expecting this, that we cannot find a bounded linear operator having this property, u composition t is equal to the identity map. Okay, so I think you got my point. So we will prove this thing by using the contradiction argument. So here let us suppose that such a function, such a operator u exists, which is a bounded linear operator. This implies what? The definition of a bounded linear operator is that there exists a constant c greater than 0 such that this condition holds for all the f belongs to the space x, and for a fixed, here the c is fixed quantity, it is independent of f, but here f are varying in the space x. Okay, this is the definition of the bounded linear operator. Now we will take an element f belongs to tx, which is nothing but our notation y. Okay, we will take an element because this image set is a subset of x. Okay, since this relation 3 is true for all f belongs to x, so this relation also hold for the f belongs to tx also. Okay, since f belongs to tx means it is an element from the image set, so this implies what? There exists an element g in the domain set so that tg is equal to f. Okay, I hope it is clear. Now the definition of tg is what? Tg is this one. If you put here x, then tgx is equal will but this, and f of x is equal with this. Okay, so for all x belongs to 0 1 close interval, then we will apply the fundamental theorem of calculus. By applying the fundamental theorem of calculus, it gives derivative. If you take the differentiation on both sides, it gives f dash x is equal with minus of g of x for x, all x belongs to 0 1 open interval. Okay, it is coming from the fundamental theorem of calculus. Also, what is given in our question, given that u composition t is the identity map. So u composition t f gives what? F, because I is the identity map. Okay, so in particular if you take the function h, u composition t h is equal to the identity map ih is equal to with h. Okay, for all h belongs to x. This is given in our question. Okay, means there exists a u which satisfy this property. Okay, so in the particular case we can take h is equal to g, then it gives what? U composition t g is equal to with g, and we know that tg is equal to what? Tg is equal to f from this. Okay, tg is equal to f, so it gives u composition f, and g is equal with what? G is equal with this one. This function is g minus f, this one. Okay, for f belongs to y. Okay, g is equal to with minus f, g is equal with minus f. This equality is almost everywhere sense, you can say, or you can write on 0 1 open interval, because since this relation is true on 0 1, therefore I am writing this, because it will not affect, because ultimately I will calculate the norm, because norm will not affect at finite number of points or the measure where this set where this measure is 0. Okay, so it will not affect in our subsequent analysis. So we can keep it 0 1 open interval, otherwise you will confuse, because this relation is true on the 0 1 open interval, but this relation you are saying that it is for all. So I am writing it is not, it may not be for the whole interval, but it at least 0 1 open interval. Okay, now I will define a sequence of functions f n x, these things, and here also you can put here you can take this whole interval. Okay, then these fn's, these fn belongs to where? Why? Because these are differentiable functions, and fn of 1 is equal with 0. Fn, if you calculate fn 1, this gives sin n pi, and sin n pi is 0, therefore it gives 0. So these are differentiable functions, and fn 1 is 0, therefore this belongs to this space y. So if you calculate the L2 norm of this, and this is nothing but this one, if you will calculate this integral value, it gives equal with 1. Then it gives fn2 is equal to, fn2 norm is equal to 1 for all n greater than equal to 1. Similarly, then you will calculate the ufn norm. Ufn norm is equal to what? Fn dash, this one, but on the g01 open interval. But and if you calculate this integral from 0 1, here we will put the fn dash, then we will find this value, this one is equal with this n square pi square, because cos square theta is nothing but 1 plus cos 2 theta, and integral of cos 2 theta cos 2 n pi is equal with 0. Okay, so it will vanish, and this gives this one, and then therefore if you take the square root on the both side, it will gives this one. Then you will use this equation 4 and 5 in equation 3. It gives what? It gives n pi, because in equation 3 is saying what? U fn L2 norm is less than equal to c fn L2 norm, but fn L2 norm is 1. This is 1, and it is n pi. So n pi less than equal to c. So it gives what? It gives n less than equal to c upon pi. But this is a very weird, very absurd thing. Why it is a very absurd? Because here n is arbitrary, so we can keep it 1000, 2000, but it is a constant quantity. So how a very large number n can be less than equal to this constant quantity? So it is giving contradiction, because this expression is true for all n. Maybe it is true for the small n, but for if you keep increasing n larger and larger, this will not be true. So it is a contradiction, and this contradiction we are getting for why? We are getting this contradiction because we are assuming that such a bounded linear operator u is a bounded linear operator. So this implies that our assumption is wrong, means u cannot be a bounded linear operator. Okay, therefore this option B is false. I hope that you all understood it very well. Thank you all. See you next time very soon. Bye bye.